Hi, I'm Yu. Today I will talk about polynomial lower bounds for parallel submodular function minimization. This is a joint work with Deeparnab, Chakrabarty, and Sanjeev Khanna. Let's first talk about what is submodular function. Given a set U, a submodular function is a set function where the variable is the subsets of U, and the value of the function is an integer, which satisfies the following condition. For any two subsets S and T such that S is a subset of T, and for any element E in U, we have Fs plus E minus Fs is at least as large as Ft plus E minus Ft. The set U is called the ground set, and throughout this talk, we denote N as the number of elements in U. Submodular function is a generalization of many fundamental combinatorial objects. For example, the set coverage function. In set coverage function, the elements of the ground set U is actually the sets, and given a set of sets in U, the coverage number is the number of objects these sets covered. Let's see this graph as an illustration. Given two sets of sets S and T, where S is completely contained in T, now given a new set E, the objects in E that are not covered by T must also not covered by S, but the reverse may not be true. So the number of new objects E covers that are not covered by T is at most the number of new objects E covers that are not covered by S, which means that the set coverage function is a submodular function. Another two well-known examples of submodular function are the mutual information of random variables and the cut size in graph. As we saw, submodular function is a generalization of many combinatorial objects. So submodular function minimization or maximization is generalizations of many combinatorial optimized problems, such as the maximum set coverage problem or the max cut or min cut in the graph. In this talk, we will focus on submodular function minimization, which is short for SFM. As the name suggested, in submodular function minimization problem, we are given a submodular function f, and we want to find the set S that minimizes Fs. And we use the query model, in which we input a set A to an oracle, and the oracle will return the function value Fa. Submodular function minimization is generalization of many fundamental minimization problems such as min-cut in graph and matroid intersection. Submodular function minimization is well known to be solvable in polynomial number of queries. In fact, it can solve by the famous ellipsoid method. There is also a long line of works to optimize the number of queries we need to solve SFM. Currently, the best algorithm is given by a recent work by Chen, which has query complexity order n square log n. However, all these algorithms are highly adaptive. In other words, these algorithms need to be run in many rounds. An R-round algorithm is an algorithm that runs in multiple rounds, and in round I, the queries made by algorithm only depends on the results of the answers in the first I-1 rounds. We also refer the algorithm that runs in one round as non-adaptive algorithms. As the scale of the real-life problem becomes larger and larger, algorithms with small number of rounds can save us many times by querying many queries at the same time. So the question is, can we solve SFM in small number of rounds while we still only asking polynomial many queries? On one hand, all current polynomial SFM algorithms runs in omega n rounds. On the other hand, it is not too difficult to show that any single round algorithm needs exponential number of queries. However, this completely changes once multiple rounds are allowed. In fact, ruling out efficient two-round algorithms already becomes much harder, and it seems that it requires a completely different set of techniques to prove such a lower bound. A recent work by Balkanski and Singer shows that Any polynomial query submodular function minimization algorithms must proceed in omega log n over log n rounds. However, their construction has an inherent bottleneck, so that it cannot rule out efficient SFM algorithm with order log n rounds. So, it might be the case that this problem can be solved in polylog rounds. In this work, we show that this is not the case. We prove that any polynomial query submodular function minimization algorithm must proceed in omega n to the 1/3 rounds. In fact, we are able to show that even a 2 to the order n to the 1 minus delta query SFM algorithms, where delta is any fixed constant, must proceed in polynomial rounds. And we also are able to show that solving SFM to within epsilon additive arrow must proceed into the order 1 over epsilon rounds. Here we assume the function value has been normalized to between -1 and 1. So in the rest of the talk, I will briefly talk about the proof ideas for the main results. In this work, we use the same framework as the previous results given by Balkanski and Singer. We consider a special group of functions called partition function. In a partition function, we divide the ground set U into R groups P1, P2 to PR, and we say f is a partition function if there is a function h whose variables is a r-dimensional vector, and fs is equals to the value of h when taking the number of elements of each group in S as the variable. We call this vector the signature of the set S, and by definition, we have fs equals to hx. By definition, a partition function f is submodular if the corresponding function h satisfies that for any two vector x and y such that x is smaller than y, then for any indices I, the partial of the ith dimension of hx is at least as large as the partial of the ith dimension of hy, where the partial of x means the function value change when we increase the ith dimension of x by 1. In the framework of Balkanski and Singer, the partition P1 to PR is chosen randomly, and we design the function h such that, first, the f given by h is submodular, and second, the minimizer of h is the vector with the size of PR in dimensional r, and 0 on all other dimensions. In other words, the minimizer of f is the group PR. The third property is that after I runs, any efficient algorithm, which means it uses polynomial queries, knows nothing about the partition of the sets pi plus 1 to PR. Thus, the first property guarantees that f is indeed submodular, and the second property means that in order to find the minimizer of f, we need to somehow find PR, and the third property says in order to do that, we need at least r-1 rounds. However, to satisfy the third property, the construction of Balkanski and Singer uses P1 to completely hide the information of the partition of P2 to PR. And to imply this idea, the size of P1 should dominate the total size of the rest sets. Similarly, the size of Pi should dominate the total size of Pi plus 1 to PR, and therefore the size of P1 should be exponentially larger than the size of PR, which implies that the number of the group R is at most order log n. So, in order to break the log n barrier, we will use a different construction to satisfy the third property. But before showing our construction, we will first introduce suffix indistinguishability, which is a property that will make sure the function satisfies the condition we want. So if a function is suffix indistinguishability, it has the following property. For any vector x such that the ratio of xi over the size of pi is similar to each other for every I, then the value hx is only depend on x1 and the sum of xi's is, in other words, the first norm of the vector x. So why this condition help us? Think about the queries the algorithm make in the first round. Since the algorithm doesn't have any information about the partition at that time, and since the partitions are chosen randomly, the queries will select a similar ratio of the elements in each group. And thus, for all these queries, because H satisfies this condition, the answer only depends on how many elements in X1 are chosen. In other words, the algorithm will have no information of the partition in P2 to PR after the first round. Then, we also require the function satisfies that for any vector x such that the ratio of xi over the size of pi is similar to each other for I larger than 2, then hx is determined only by x1, x2, and the norm of x. So in the second round, since the algorithm has no information about the partition in P2 to PR, the queries will choose similar ratio of the elements in P2 to PR. And by suffix indistinguishability, the algorithm will not learn anything in P3 to PR after the second round. Similarly, for any I, we require that if the ratio of the elements in Pi to PR is chosen similarly, hx is only determined by x1, x2 to xi and the norm of x. Then, in round I, the algorithm will learn no information of the partition of pi-1 to PR. And thus, as a result, we need at least r-1 rounds to figure out PR. And this concludes the definition of suffix indistinguishability. As long as the function h has this property, then any algorithm will need at least r-1 rounds to figure out PR. Now we show a simplified version of our construction of the function h and show why it satisfies the suffix indistinguishability. In our construction, each group has the same size n, which equals n over r. Given a vector x, we define the function Lix to be the sum over all j at least I, xj minus n over 2. And let A and B be two indices that give the largest and the second largest L values. Then, we define hx to be the sum over all xi minus maximum 0 and Lax and the maximum over 0 and Lbx. Let's see an example. Suppose n equals to 8 and r equals to 7 and x takes the value 3732657. Then L7x is 7 minus 4, which is 3. L6x is 7 minus 4 plus 5 minus 4, which is 4. And by the same way, we can calculate L5x is 6, L4x is 4, L3x is 3, L2x is 7, and L1x is 5. By definition, A and B are 2 and 5, and both Lax and Lbx are 6. So the value of hx is the norm of x, which is 33, minus 6 minus 6, which is 21. Let's see another example. Suppose now x equals 3, 7, 2, 2, 6, 1, 2. Then by definition, the value of Lix's are minus 5, -4, -7, -5, -3, -5, and -2. Then by definition, A and B are equals to 5 and 7, and LAX equals -3 and LBX equals to -2. And since both of them are less than 0, so the value of HX is just the norm of X, which is 24. Now, let's see why this H satisfies suffix indistinguishability. First, let's review what is suffix indistinguishability. It says for any I, if xi over the size of pi is similar to xi plus 1 over the size of pi plus 1, similar to all the way to xr over the size of pr, then hx is determined by only x1, x2 to xi and the norm of x. Now for simplicity, suppose xi to xr are all the same. Then we consider two cases. If they are all larger than n over 2, then we have Lix larger than Li plus 1 x larger to all the way to Lrx. So by definition of A and B, they are at most I and I plus 1, since they are the largest among the indices that are at least I. Note that Lix only depends on the sum of Li to Lr, and Li plus 1x only depends on the sum of Li plus 1 to Lr. So the value of h only depends on x1, x2 to xi and the sum of Li to Lr, which implies it satisfies the suffix indistinguishability. Another case is when they are all smaller than n over 2, and in this case, all the L values for indices larger than I is 0. So no matter A and B are among them or not, these L values does not affect the H values, which implies that the function still satisfies suffix indistinguishability. So we can see in both cases, the function has this probability we want. And this concludes the main idea behind our construction. Finally, it is worth to note that our lower bound result can also be used to prove the round complexity of matroid intersection as well. And we prove that any polynomial query algorithms for matroid intersection that using rank queries must proceed in tilde omega n to the 1 over 3 rounds as well. And here are some open problems. First, since all the current algorithm needs order n rounds, is it true that the lower bound of the round complexity of SFM is really omega n? Or is there a polynomial algorithm that uses only n to the 1 minus delta rounds? On the other hand, for fully adaptive SFM algorithms, the upper bound is n squared and the current best lower bound we have is omega n. So the question is, can we show an n to the 1 plus delta lower bound on the query complexity of SFM, or there is an algorithm that only uses near linear number of queries? And thanks for listening.